So hi everyone, my name is Nora Abiakar, and I'm going to be presenting the next use case. I am a software engineer at CSCS. I work on a project called Arbor. It's a simulation library for neuronal networks, and actually this use case is part of the Arbor library. It's a multi-threaded task system, which is its own isolated part of Arbor. So it's its own library that's part of the project. I've used as resources for the talk and also the library itself, a talk by Sean Parent called Better Code Concurrency. I think it's available on YouTube. I recommend it if you want to go take a look there. This presentation is more focused on the C++ implementation of that. Okay. So this is a brief outline of what I'm going to be covering. First, I'm going to talk a bit about why we would want to use a task system. Then I'm going to focus on the implementation and the design, starting with a single queue implementation and moving on to multiple queues. I'm going to show a bit a performance comparison with existing libraries on the market. And then we're going to talk about exceptions. How to handle them as part of the the task system, the multi-threaded task system, and how to achieve an early exit in case of an exception. Finally, we can have some questions, but if you want to interrupt as well in the presentation, feel free to do so. All right. So why would we want to use a multi-threaded tasking system? In Arbor, in our application, we have we have many tasks that we want to execute. These tasks have varying sizes, but they are independent, which means they can execute concurrently and in parallel. And in HPC, usually people go for the approach of launching a single MPI process per core. So for example, on PIDSDINT, we would have a single node has 2 sockets and each socket has 18 cores on the multi-core partition, right? So people in HPC might be tempted to go and launch 36 MPI processes on a single node on PIDSDINT. But you could do the opposite thing. You could launch maybe 1 MPI process per socket and then have these 18 threads per socket per MPI rank kind of working together and executing tasks in parallel. And this is why we would want to use a multi-threaded tasking system, because sometimes that's the better approach than using MPI everywhere. And the requirements for the tasking system in general, but also specifically for our case, were that we want to utilize the machine resources fully. Right? We don't want any cores on a node to be idle waiting for work. We also want minimal overhead of the system because we don't want to spend all of our time basically managing the tasking system. It needs to basically have 0 overhead so that all of the time is spent executing useful work. Another 2 things that we care about is basically exceptions. We want to correctly handle the exceptions so that if an exception is thrown in the task system, it's correctly propagated back to the user. And if we have an exception, we don't want to continue running all of the tasks in the system. We want to exit early because all of the other tasks, they don't matter. There's an exception, something went wrong, we need to fix that. And finally, we didn't want to use an external library. There are a lot of external libraries that could function as a task system or that are an implementation of a task system. But we try to keep our code base kind of isolated. We don't use a lot of external libraries. So we wanted to write our own thing. But of course, we didn't want to write something huge. We wanted to keep it simple so that we can maintain it essentially. So that's why we wanted to write our own tasking library. And we were able to kind of satisfy all of these requirements by implementing multiple task queues and running that on a thread pool. And this will be the focus of this talk, how to implement this. Before I jump into the implementation, I'm going to show a few examples of how we would want to use this task system in the end. These are some kind of dummy examples. They're not really doing any useful work, but they kind of illustrate how to use the API. So we've got two vectors. The first vector v0 is a vector of integer, and it has size n, and it's initialized to -1. And the second vector v1. By the way, can you see my cursor when I'm moving it on the screen?
Yes.
Yes, we can.
Okay, perfect. The second vector v1 is a vector of integers, and it has size n by m. Both of them are initialized to -1 initially. And we want to go ahead and initialize them. We want to set v0 of I to I for all of the members of v0, and v1 of ij to I plus j. And to do that, we're going to use the tasking system that we're going to build. So we're going to create our task system, and then we're going to use a parallel for loop. And the way we use it is we call parallel for, we apply from 0 to n. So these are the limits of the for loop. We iterate from 0 to n. That's the size of vector v0. And we're going to give a pointer to the task system. And then the actual task that we're going to execute is represented by this lambda, where we capture v0 by reference, and we have an argument I, and what we're doing is we're setting v0 of I to I. This parallel for loop will automatically generate the integer I from 0 to n, and that's basically how we will initialize v0 in parallel. We will initialize v0 of I equals I in parallel. For v1, we can do something a bit more interesting maybe. We can initialize it in a nested parallel for loop. So we do parallel for apply from 0 to n, and this is like the outer parallel for loop. And the lambda, so the task that it's executing, is itself again another parallel for loop, which loops this time from 0 to m, and everything is kind of captured by reference. So we can do v1 of ij, or w of j is I plus j. And that will basically be how we plan in the end to use this tasking system, or what we can do with this tasking system. Once we return from the function here, each of these parallel for loops, we know that all of the tasks inside have been executed. All right. So as I mentioned, there are a lot of existing libraries that do this. For example, Intel TBB, HPX, they're both open source and support many platforms. There's also PPL, libdispatch, many others, of course, that can be used. So this talk isn't kind of to tell you that you should go and build your own multi-threaded tasking system, but it's more of a reference implementation, and it's really interesting as the use case, actually. Okay. Before we jump in again to the design and the implementation, I just want to go over some of the classes and functions that I'm going to use from the standard library from namespace std. I'm going to be using std vector. I think this is quite common. Most people know std vector. I'm also going to be using std deck. So this is a first in, first out data structure, and that's going to be how we implement our queues using std deck. We're going to be using also std function. I think this was introduced earlier in the course, but we don't really need to know much about it. It will come up in the context what we need to know about function. But basically, this will be how we represent tasks in the tasking system. Then there is exception pointer. Again, we don't need to know too much about this, but this will be how we represent exceptions in our system. Then from the threading part of the standard library, we're going to be using std atomic, mutex, and unique lock. I won't describe all of these, but again, it should be very clear how they're used. And we're going to use Std Thread. That will be a singular thread in our threading library will be Std Thread. So that's what we're going to use. And Std condition variable. Condition variable, this, I don't know if most people know about it. There is a slide kind of describing how it works. So we'll get to that in a moment. Finally, we're also going to be using std move, forward, and decay to kind of make sure that we don't copy things when we don't need to. So this is most of the stuff I think that we're gonna cover in this presentation. And just as a note, I don't use std : everywhere. In fact, I think it's rarely used, just to keep the code snippets short. But yeah, I wouldn't recommend to use namespace std globally because that's not good practice. But the only reason it's not there is just to keep things kind of short and clear in the presentation. All right. So I've copied here the page on Std Thread from cppreference.com, just to do a little bit of a recap on how that works. And so a thread, the class thread, represents a single thread of execution. So it's basically just, it works like a single thread allows us to run some functions, and multiple threads can be running at the same time. So multiple functions can basically execute concurrently. And when we construct a thread, we have to give it a constructor argument, which is a function. And as soon as the thread is constructed, it automatically begins executing the function that is in its constructor argument. So that's how threads start working. And when a thread finishes executing that function, it returns, the function returns, and the thread can be joined, which means that the thread can be safely destructed after that. Okay, so not much to know about thread. It will be very obvious how it works in the code. Condition variables, on the other hand, they're a little bit, there's more info to know about them to understand how they work. And a condition variable is a synchronization primitive, and it can be used to block a thread or multiple threads until another thread comes in, modifies some shared variable between the threads, and then notifies the condition variable. So the condition variable acts as sort of a mediator to allow the threads to communicate with each other in a sane way. And when dealing with a condition variable, a thread can do two things. It can try to modify a variable, and it can try to wait on a condition variable. So if it wants to modify something that's shared between the threads, what a thread needs to do is first acquire a mutex, and then perform that modification while the lock is held. And then it needs to notify all of the other threads that something has changed, that the shared variable is changed. And so the reason it needs to notify the threads is because some other threads can be waiting on a change to happen to that shared variable. Which brings us to the wait, right? Because some threads can be waiting for something to change. And if they want to wait, they have to, again, acquire a mutex first, then execute the wait or wait for or wait until calls. And when you execute wait, or when the thread executes wait, it automatically releases the mutex and blocks. It just stops working, and it waits until it is notified by some other variable. So when another when another thread calls notify one or notify all, the condition variable is notified, and the thread is reawakened. And when it is reawakened, it automatically reacquires the mutex, and then it can check why it was notified and do whatever work it needs to do. So this is maybe a lot of information. We'll come back to this, and I will describe how we use the condition variable when we get to it. But I thought it's a good idea to kind of go over the CPP reference page, because it highlights pretty much all you need to know about it. Okay, so finally, we can come to the design and implementation of our system. And we're going to start by designing a tasking system with a single task queue. And this is what it's going to look like. We're going to have a queue here full of tasks of varying sizes. And we're going to call this a notification queue. It's going to be a special queue that we're going to have to implement as a class. And we're going to have a bunch of threads that are executing these tasks in parallel. We're going to call this our thread pool. And together, the notification queue and thread pool are going to be maintained by our task system. Yeah, so this is a bit of a different view of things, like a block diagram to kind of illustrate the internal and external APIs that are going to be used. So at the moment, the async function, this is the function that the outside world uses to interact with our task system, and everything else is kind of internal. The task system manages that. By the way, the solid black line here indicates motion of data, whereas the dotted black line indicates control. So the function async, it basically pushes a task onto the task system and tells the task system that it needs to execute this task. And then the task system is responsible for dealing with this task. And what it does is it pushes the task onto the notification queue. And when it pushes it, it indicates that this is something that needs to be executed. When the notification queue has some tasks, it can receive a pop call from the thread pool. And the thread pool is basically asking for something to execute. In which case, the notification queue will give it some task, which the thread pool will deal with, and then it can move on and try to get another task. The task system can also tell the notification queue that it's time to quit, which means the notification queue is expecting to receive 0 more tasks, so it's only supposed to execute the tasks that it already has. And it can also control the thread pool by telling it, okay, now I'm going to create some threads, you have to start working, right? Okay, so these are basically the functions that we're going to try to implement: async, push, pop, quit, and run tasks. We're going to implement the notification queue as a blocking concurrent queue, and we're going to implement it as a special class. And the thread pool is just going to be a vector of Std Thread. Okay, so we get to the actual C++ implementation. And I'm going to start with the task system. So we've got a task system. It's a class. It has 2 member variables, a vector of thread called threads underscore, and a notification queue. We're going to take a look at the implementation of this in a second. And it has 4 methods: a constructor, a destructor, and 2 functions, one that's called run tasks loop and the async function. And we're going to go over each of these separately. First, I'm going to be using some aliases. Lock is going to be a unique lock of a mutex. It's just going to be used to lock the mutex in a moment. And we're going to be using task to be a function of void empty parentheses. So our task is basically expected to be a function which has 0 arguments and returns void. That's what the task system expects to get in. And we talked about the vector of threads and the notification queue. These are the components of the task system, the members of the class. And we get to the constructor. So the constructor takes in as an argument the number of threads in the thread pool. And it goes ahead and it creates n threads minus 1 new threads. Why not n threads? Because the main thread, so the thread that actually goes and constructs the task system, is expected to take part in the execution of the threads in the queue. So we only need to create n threads minus 1 new threads. And we do that by calling the InPlaceBack function on the std vector, which basically constructs a vector and gives it this lambda as the function that it's supposed to run. So the function that it's supposed to run is essentially run tasks loop. So each thread, when it's constructed here in this constructor, it will go ahead and it will start running this function immediately. As for the destructor of the task system, we're going to do 2 things. We're going to tell the queue that we are now in a quit state. We no longer expect to push any more tasks onto the queue because we are destructing the entire task system. so the queue can go ahead and clean up what needs to clean up. And for each of the threads, we are gonna call the join method. What this does is when this task system destructor is executed, for each of the thread, it's gonna wait until the thread finishes the work. If we go back to the constructor, the work of the thread is this run tasks loop. So when we join, we wait until run tasks loop successfully returns. And we do this for each of the threads because once all of the threads are joined, we can safely destruct all of the threads in the task system. And this is what happens. All right. Now that we're done with the constructor and destructor, we can take a look at the run tasks loop function. And again, this is the function that is executed by each of the new threads in the system. And because the threads are expected to always be executing tasks, right? We don't want to create a new thread per task in the system. We're gonna run a while true loop in this function. So it's always gonna be running until something breaks it. In the usual case, we're gonna create a task from, we're gonna actually pop a task from the queue. So queue.pop will return a task. If the task is an actual task, if it's not empty, we're gonna go and execute it and then go back to the top of the loop, pop another task, execute it, so on and so forth. We only break out of the loop when queue.pop doesn't return back a task or it returns an empty task. And this signifies to us that there are no more tasks in the queue and that we don't expect that there will be any more tasks in the queue. So this is when we destruct the entire task system. In that case, the thread breaks out of the while loop, the run tasks loop function returns, and the thread can be joined in the end, and the task system, the whole thing, can be destructed. All right, hopefully so far it's clear. That leaves us with the async function. And the async function, if you recall, that's how the outside world can push tasks onto the task system. And so it takes as an argument a task. And then it goes ahead and it pushes the task onto the queue. And we use std move because we want to avoid copying the task if at all possible. All right. So with that, we've basically finished the implementation of the task system. But we haven't looked at the notification queue itself. We used these three methods already, pop, push, and quit from the task system. So we need to take a look at how they're implemented. We're still using the same definition for lock and task. And now we can take a look at the members of the notification queue. So we've got a deck of tasks. This will be the actual data structure that holds the tasks for us. We're going to need a mutex to control access to the deck because it's not thread safe. We're going to need a condition variable to allow the threads to communicate with one another, or to allow the threads to, we'll see, or to allow the threads to kind of control access to the queue. And we're going to need a Boolean quit, which tells us whether or not we are in a running state. And it's initialized to false because initially we are in a running state. We want to pop and push tasks from this queue. Okay, so what does the pop method look like? The pop method is supposed to return a task, right? Yeah, basically it. So we start by creating an empty task called TSK. And the first thing we do after that is we lock the mutex. Why do we need to lock the mutex? We need to lock the mutex because we want to modify this queue in some way, and we need to lock the resource because it's not thread safe otherwise. So we acquire the mutex, and then we go and check whether our queue of tasks has tasks in it. So we check whether or not it's empty, and we check whether or not we're in a running state. So in the case where there are no tasks to pop out, and we are still in a running state, so we expect that there will be tasks in the future, we need to wait. We need to wait until either there's a new task in the queue, or we are no longer in a running state, we're in a quit state. And only if these two conditions are true can we return an empty task, if we're in quit state and the queue is empty. Okay, so let's say we go in and we check and the queue is empty, so we have to wait. What happens after we wake up? After we wake up, it could be because the queue is empty. It could be because, it could be because the queue is no longer empty. It could be because we are in a quit state. But we do actually need to check these conditions again, because we could wake up for neither of these reasons. We could wake up by mistake. So the thread goes and it checks these conditions in a while loop. It needs to keep checking until it's sure that the reason it woke up is because there are tasks in the queue or because it quit. And so if it breaks out of that while loop, it's certain that one of the two conditions is true. So if the queue is not empty, it means that it can actually pop a task out of the queue and then execute it. Well, not execute it, the thread will be able to execute it. So if it's not empty, we will move the task from the front of the queue and pop the front, and then we will return it. But if we check that the queue is empty, so if condition here is false, we know that the only reason we were woken up is because we are no longer in a quit state, in a run state. So we're in the quit state. If we're in the quit state and there are no more tasks to be run, we return an empty task. And so we know if pop returns an empty task, then the thread can finish its work and it can be joined. All right, that's the pop function. Yeah. If you have any questions, please stop me. I don't think I can see the chat, so yeah, feel free to just say something. All right. Now we move on to the push function. And the push method takes as an argument a task. And the first thing it needs to do is, again, to lock the mutex, because it intends on modifying the deck. So it locks the mutex, and then it basically just moves the task onto the queue. And the reason we do this between these braces is because we're scoping out the lock. So once we exit the scope of the brace, the lock will be automatically released. It's just a design choice. It's nicer than to explicitly release the lock. And then once we have pushed a task, we need to call notify all on the condition variable. And once this notify all is called, this is what wakes up a thread that's waiting in pop. So the thread wakes up and then it needs to check, oh, is there actually a task in the queue or not? And then it can either go back to waiting or it can move on. Quit is very similar to push. We need to acquire a lock. To modify quit, we just set it to true. And then we need to notify all of the threads again, which in pop will wake up a thread that's waiting in here. And that's all there is to it, essentially. This is how we create a tasking system with a single queue. And this is what we end up with. We end up with a single queue that has a mutex that needs a mutex to be acquired for any task to be pushed on and popped off from the queue. And this can actually cause a bit of an issue. This mutex synchronization adds quite a bit of a serialization overhead, especially when we are popping out of the queue. To better visualize this, let's think of a queue that has many short tasks. And the threads want to execute all of these tasks. So the first thread here acquires the mutex and it gets a task. And as soon as it gets a task, it releases the mutex, which is acquired by another thread, which does the same thing. And the mutex keeps moving around, right? But if you notice, the green bubble here, it represents when the task is running. And if you notice, no two threads are green at the same time. And this is because the cost of locking a mutex, of acquiring a mutex, is basically too high, so that the execution of the tasks is basically no longer happening in parallel. The tasks are too short. The time is basically equal to the time it needs to acquire the mutex. So, sorry, in the end, we end up basically running tasks sequentially, but over several threads in the worst case. And that's not good. We don't want to end up in the situation where just using a mutex is already taking up so much time, and it's basically a huge overhead in the task system. So to fix that problem, we're going to implement multiple task queues. And the point behind this is that every thread will have its own dedicated task queue, so that it doesn't have to fight with other threads to get access to the queue. For that, we're going to need a scheduler at the top, because now when we push a task into the system, it needs to go onto one of n queues. So we need a level of scheduling. But there's still one more problem that could happen here. Because tasks can be of different sizes, we could end up in a situation where the first queue, for example, has many short tasks, and all the other queues have many long tasks. So thread 1 here can finish all of the tasks in its own queue, and then it can be idle, whereas all of the other threads have a bunch of work to do and they're very busy. So what we would like to do is for thread 1 to participate in executing some of the tasks from the other queues. So we need a second level of scheduling here, so that thread 1, for example, can steal a task from thread 4's queue. And so with that, we end up with a pretty good way, or a pretty good implementation of a tasking system, where we avoid the mutex synchronization problem, in the most part at least. We're still going to be implementing a single queue as a notification queue. We're just going to be changing the class a bit. And we're going to have multiple of them in the task system. The thread pool is still a vector of threads. And the task system now basically has a bunch of threads and a thread pool. I saw someone raise their hand. Would you like to ask a question?
Yeah, hi, Nora. Actually, what I want to ask is, like, when you were saying that, okay, probably the thread 4 has a lot of tasks and thread 1 can steal some of them from thread 4. But how do you know that in thread 4, all the tasks are not in the middle? Like, while stealing, you have to know that if the tasks are in the middle of something or not. Because if it has not yet started, then you can steal.
Yeah.
If it has already started in the middle of something, how do you check that?
So if it's already in the middle of execution, the task will not be in the queue. It will be popped off of the queue, handed off to execution by the thread. So no task in the middle of the queue will be in the middle of execution.
Okay, thanks.
Okay. I can go back and show how that happens actually, because, oops, sorry. Okay, so it's in the task system. I went back quite a bit, but you can see here that you pop from the queue, you return a task, so that task is no longer on the queue, and then you execute it. Okay, so if it's already in the process of being executed, it's no longer on the queue. Okay. All right. So we can move on to another look at the block diagram of the system. We've got the same functions: async, push, quit, pop, and run tasks. But now we've got try push and try pop, and we have multiple notification queues. And try push and try pop are basically optimistic methods. You just try to do something, either push or pop onto the queue, and you have the possibility to fail. Whereas push and pop were kind of like blocking functions. If you fail to pop a task, that means there are no more tasks in the queue to pop, and you can't really fail to push a task onto the queue. So how would we modify our notification queue to work in this new system? We still have the same functions, pop, push, and quit. We still have the same members, but we add two new methods, try pop, and try push. Okay, so what does try pop look like? We're gonna create an empty task in the beginning. And then we are going to only try to lock the mutex. Before, we were forcefully locking it. That means if the mutex is not available, we are going to wait until it's available and we can lock it. In this case, we are just going to attempt to lock it. That means if the mutex is available, that's great, we're going to lock it. Otherwise, we're just going to skip this entire thing because if qlock will be false, so we're just going to return an empty task and try pop will have failed. The hope is because each queue kind of has its own dedicated thread, that most of the time the mutex will be free. And most of the time we will be able to just try to just acquire the lock on the first try. So most of the time, this queue underscore lock will be true. And then we just have to check whether there are any tasks in the queue. And if there are tasks in the queue, then we're just going to get a task from the front of the queue and pop it. That means remove it from that queue. And then we're just gonna return the task. And the hope is that try pop most of the time will be successful. And most of the time it will just be able to acquire the lock. Similarly, for try push, we are just going to try to acquire the lock. And if we're not successful, we're immediately going to just return false, saying that we were unsuccessful in pushing a task onto the queue. If, however, we are able to acquire a lock, we're going to move the task onto the top of the queue and notify our variables as before, and then return true to indicate that try push was successful. So that's really all there is to the changes to notification queue. The task system also has some changes onto it. The main one being that we no longer have just a single notification queue. Now we have a vector of them, one per thread in the system. And also we're gonna have an unsigned variable called count to keep track of the total number of threads, which is also the total number of queues. And we're gonna have an atomic unsigned variable called index. And index will be initialized to 0, and it will be used to keep track of the total number of tasks pushed on all of the queues. And this atomic unsigned variable is going to be used to schedule where each task goes. So when you try to push a task, on which of the queues in the system the task will go. All right. So let's see how the constructor of the task system will change. Now we are going to just initialize count to the number of threads to save the number because we're going to need it. And we are going to construct a vector of notification queues. So n threads, new notification queues, and they're going to go in the vector q underscore. Cool. So we've got our vector of notification queues constructed. Now we need to construct our thread. Our vector of threads. So again, we construct count -1 or n threads -1 new threads. And it's still the same, except that run tasks loop, before it had no arguments, now it has an argument I. And I will be the index of the queue that is dedicated to each of the new threads. So thread 1 will have q underscore at 1 dedicated to it, and thread 2 will have q2, etc. For the destructor of the task system, it's still the same, except before we were just quitting on a single queue. Now we need to quit all of the queues. And we get back to the run tasks loop. So as I mentioned, now it has an argument, which is the index of the notification queue and the vector of notification queues. So what are we gonna change? We're gonna start by constructing an empty task like before. And now what we're gonna do first is we're just going to optimistically try to pop from first our own dedicated queue. And then if we are unsuccessful by popping from our own dedicated queue, optimistically using try pop, we are gonna try to steal a task from another queue. So this is what this for loop is representing. We are gonna loop over all of the queues in the system by looping from n equals 0 to n equals count. And we are gonna try to pop from each of the queues, starting with our own dedicated queue at index. So this is what this formula is doing. We are round robin going from our own dedicated queue to all of the other queues, optimistically trying to pop from one of them. The hope is that we will immediately on the first iteration of this for loop get a task, break out of the for loop, and immediately execute it. So we just want to go here, here, and here to execute the task. If we fail on our dedicated queue, we hope that we'll be able to steal a task from somewhere else, and again, break out of the loop and execute it. If, however, for some reason, we go over all of the queues in the system and we are unable to optimistically try to get a task from one of them. In that case, TSK will still be empty, so we will forcefully pop a task out of our own dedicated queue. So queue underscore at index. And as before, the only situation in which pop will return an empty task is if there are no more tasks in any of the queues or in this dedicated queue, and we don't expect there to be any more tasks in the queue. In that case, the task will be empty. We will break out of the run tasks loop, and the thread can be joined and it can be destructed. So that's basically it for run tasks loop. Async is also a bit different because before we were just pushing onto the single queue in the system. Now what we want to do is we want to schedule the task to go on one of however many queues we have in the system. And we want to use a round robin way. That's how we decided to implement it. So to do that, we just keep track of the total number of tasks pushed on all of the queues. We increment it every time we get a new task. And then we use this index to basically push a task each time on a different queue, moving over the queues in a round robin way. And this is actually what we do. We start with queue at I modulo count. But what happens if we try to push on that queue that we have chosen? If we try to push and we fail, then we're gonna check the next queue. So we start at I modulo count, then we're gonna go to I +1 modulo count, then I +2, until we've tried to push on all of the queues and failed each time. If that happens, then we are going to just, sorry. So if we are unsuccessful in just optimistically trying to push on all of the queues, then we are going to force a push on I modulo count, right? So on the original one that we wanted to push on. And then we can finish. However, if we successfully push on one of them, then we can just break out of the for loop early and return. So hopefully that is clear how we do the scheduling for pushing the tasks and how we do the task stealing in the system as well. Okay, so now we have a new method that I hadn't mentioned before, which is called try run task. And this method is used to just try to run tasks. And why do we need this? For that, we have to go back to the constructor of the task system, right? And when we started in the beginning, I said we create only n threads minus 1 new threads. And these new threads will be running run tasks loop. And I said that the reason we don't create n threads new threads is because the main thread, the one that calls the constructors, the one that kind of is running the main thing, is also going to participate in running some of the tasks in the queues. And the way that it does that is that it runs this function, try run task somewhere in a loop. And this is handled elsewhere. We'll get to that in a moment. So try run task will, like the name suggests, just try to run a task, and it can fail. What it will do is it will just utilize the try pop function here, and starting from thread 0, from queue 0, which is the queue dedicated to the main thread, it's going to try to pop a task. If it's successful, it will execute it, break out of the for loop, and return. If it's unsuccessful, it will just go to the other queue until it's visited all of the queues. And if it's still unsuccessful after all of that, it will just return without having executed any tasks. And yeah, this is unlike run tasks loop, which is a while true loop. Try run task is just trying to execute one task, so there's no while true loop. And yeah, we're going to see in a moment how this try run task function is used. Yeah, but until then, we're going to get to task groups in a minute, but I just want to take a moment to say that that's basically the full implementation of the task system with the notification queues. So that's great. We finished the first part. But if you notice, the task system itself as a class is quite limited. We only have the async function to allow us to interact with the task system, right? Which means we can only push tasks onto the task system, but we have no idea when they're executed, right? So I can push 10,000 tasks. I know they're going to be executed at some point, but I don't know when. I don't know when any of them will be executed. And that's not very useful, which brings us to the concept of a task group. Because very frequently, actually always, I think, we need to be able to know when tasks are done. Because we need to serialize groups of tasks. For example, we want to make sure that every task in blue here has been executed before any of the tasks in purple can start. There's some synchronization issue that forces that to happen. So what we want is some way to wait on a task of groups to be done, on a group of tasks to be done. And so we come up with the concept of a task group, which is one more layer of abstraction, one more class that we have to implement that uses the task system along with some other functions to guarantee that a group of tasks has been executed. And yeah, basically it gives us a way to wait on a group of tasks. And yeah, this is what the block diagram will look like. Now, the async and the try run task function that we just discussed are the internal API, and it's going to be used by the task group to expose a better API to the user. And this API will be composed of run and wait. Run basically pushes tasks onto the task group. It tells the task group that these need to be executed, so the task group just forwards it to the task system. But then there's also a wait function. And when we call wait on a task group, wait will block until all of the tasks that were previously run have executed, and then it can return. Okay, so how is this task group implemented? We've got as members an atomic of size t, of type size t, called in flight. And what InFlight will do is it will keep track of all of the tasks in the group that have been unqueued. So we have already said we wanted to run them, but we have not run them yet. It will start with 0. It will go up to however many tasks there are in the group. And then as we execute the tasks, we will start to decrement it until it goes back down to 0. And of course, the task group needs some sort of way to access the task system, so it has a pointer to the task system. And when we construct the task group, we will just give it a pointer to the task system, which was constructed externally, and it will go ahead and save that pointer. And then when we destruct the task group, we're just going to call the wait function. So before we delete the task group, before we destruct the task group, we want to make sure that all of the tasks that we already ran or we already include onto the task system have been executed. All right, so what does this wait function look like? It's very simple. We are going to be spinning on InFlight. So while InFlight is not 0, while there are tasks to be run, we are going to wait. And while we wait, we are going to try to run tasks. So this is where try run task basically comes in. While the main thread is waiting to finish the tasks for the other threads to finish executing the tasks, it's going to go in and it's going to try to help by running tasks of its own. And that's all there is to it. As for the run function, what it's going to do is what it needs to do actually is to just forward the task onto the task system, right? And we have the async method of the task system to do that. Also, it needs to increment InFlight because it needs to keep track of it in InFlight. But there's something extra that needs to be done in the task system now. The task system before, when it executes a task, when a thread executes a task, all it does is just execute the task, right? It just calls F with the parenthesis operator and that's it. But now we need something extra to happen. We need, as soon as the function is executed, we need InFlight to be decremented. And so we need to do something special here. We need to wrap the function itself, the useful task, along with InFlight into some new object, which when executed, will both run the function, run the task, and decrement InFlight at the same time. And this is what we're doing. We're gonna create a new object by calling this make-wrapped function. And then the output of the function will be an object which will be passed on to async and pushed onto the task system. Yeah, that's what we're gonna have to do, and that's what we're gonna look at next, this make-wrapped function. Just as a note, the f ampersand here, the type of the argument to the run method, this is called a universal reference. And this is why we use std forward here. I'm not going to go too much into detail, but I will say that std forward here in combination with a universal reference makes sure that the function f here, small f, is moved when necessary and copied when necessary. So if f is actually an R value reference, it will be forwarded as an R value reference. If it's an L value reference, it will be forwarded as an L value reference. And this is why we need std forward here. Okay, so the missing part of the picture is this make-wrapped function. What is it actually? So what it's doing, make-wrapped function, you can see it here in the bottom, is it's actually creating an object of type wrap. So this is wrap here, it's defined here. It is a class which has a function f with type name f. And so this will be the task, it will be stored here, and it has a reference to an atomic of type size t. And this will be the in-flight atomic from before. So let's go back a moment. Make-wrapped function takes in a function f and in-flight. And make wrapped function here takes in the same thing, a universal reference to f, and a reference to the atomic size t. And then it basically just calls the constructor on the wrap class and forwards the stuff in the same way again. And then we can go and construct the class, right? Just as a note, you will notice here that wrap is templated on callable of f. And callable is the standard decay of f, quote-unquote type. So the type of the standard decay of f. Again, I won't go too much into what standard decay does. I'll just say that it kind of removes the references of f so that we create the wrap object with the correct type. We don't want the references to be there. So we are creating a new object. We're constructing a new object of type wrap. So we're going to be calling exactly this function. And we're just going to forward the function and save the reference to the counter. It's also a very good practice to create your copy and move constructors. It's actually kind of necessary here because we don't want to copy functions if we can avoid it, right? We don't want to copy this wrap class if we can avoid it. We want to move it always to reduce the overhead of the system. But what really matters here, the main reason why we created this wrap class is so we can write this parenthesis operator. Because now when we execute an object of type wrap, we are going to execute the internal function f underscore, and then we are decrementing the counter. And this is exactly what we want to do so that the in-flight counter in the task group can eventually make it back to 0. All right, so that's basically it. I know it's a lot of information, but I hope it's interesting. So now we can talk about the performance of this task queue, of this system, I mean. Here I have, I'm comparing the implementation of a single queue task system and a multiple queue task system to TBB. And on the horizontal axis, we've got the size of the tasks in microseconds. And on the vertical axis, we've got the efficiency, which we want to be as close to 1 as possible. And we can see that the single queue implementation is actually not so great, right? It has quite a low efficiency, except when we get to really large tasks. And this is anticipated, right? This is why we went to the multiple queue implementation. The multiple queue implementation, on the other hand, seems to be doing much better for medium to large size tasks. And that is good news, because it turns out in Arbor and our library, we only care about tasks that are medium to large sized. TBB still outperforms us for small tasks. It's not surprising as well. It's much more complicated. But we don't really care for those small task sizes, so we can just use our own implementation, and we do. All right, let's move on. So let's go back and look at our requirements from the beginning. We wanted our machine resources to be fully utilized with minimal overhead, and I think that the performance comparison proves that we were able to do that. We don't have an external library, we wrote our own code, and it's quite short and not too complicated. It's actually less than 200 or 300 lines actually altogether. But we still haven't spoken about exceptions. We want to be able to handle exceptions correctly. So any of the tasks in any of the queues can always raise an exception, right? And we want to, when an exception is raised, we want to do two things. We want to be able to propagate it back, so we want to handle it correctly, and we want to ideally exit early. We don't want to go on and execute all of the other tasks because there's no point. However, we do have some leeway, some things that will make our synchronization constraints easier. And these are that if an exception occurs, we don't need to stop immediately afterwards. We can run a few extra tasks. It's not a big deal. This will relax our synchronization constraints. And also, we don't care which of the exceptions that are created is returned. It doesn't really matter. The order in which the tasks are executed depends on, the threads and, race conditions, etc. So we just return any of the exceptions that we get. And we're gonna use this info to handle exceptions correctly. And we're gonna do this in the task group, actually, separately from the task system. So we need to go back and look at the implementation of task group. And we are gonna add a new member called exception status, which has the type exception state. This is a new class, which we'll have to also implement. And we're gonna modify our run and wait functions. So how does wait change? Before, we were just waiting on in-flight to be 0. Now, after in-flight reaches 0, we need to check that whether or not an exception was raised. And we do that by calling exception status.reset, and we expect that reset will return an exception if there is one and reset it back to 0 as well in the class here, in the object. So we check whether there was an exception, and if there is, we just rethrow it. And that's all there is to it, really. As for run, now we have to do something a bit different. So we created this make wrapped function because when we ran f, we wanted at the same time to decrement in flight. But now when we run f, we not only want to decrement in flight, we also want to set the exception status if something goes wrong. So we have to go back and fix this wrap class. We have to forward the exception status basically to the parenthesis operator. So how does wrap get changed? We're gonna pass the pointer to the pointer to the exception state to the constructor, which is gonna save the reference to it. And then we need to change the parenthesis operator. Before, if you remember, all we were doing here was executing f and decrementing the counter. But now what we're going to do is we are only going to execute f if no exception has occurred. If an exception has occurred already, we are just going to decrement the counter and go on without executing the task at all. So that's how we kind of do an early exit. We just decrement the counter down to 0 without executing any of the tasks after the first exception has occurred. And now, if there is no exception status, we're just going to run the task, but we're going to do it in a try catch block. And if the function raises an exception, it will be caught and set into the exception status. So that's all there is to it. Now, all that's left is this exception state. What is it? It's a class or a structure, which has an atomic of type Boolean, which is called error, which tells us whether or not there is an exception that has happened. There's going to be an exception pointer to store the exception, and a mutex, because we're going to be altering exception pointer, and we need to do it in a thread-safe way. So the first function we're going to do is the cast to Boolean, because I'm going to go back quickly. Here in exception status, we check whether or not it's true. And to do that, we're going to need to be able to cast it to a bool. And this is what happens here. We're just going to return the value of error. And we're going to do that by error.load with memory order relaxed. I thought about kind of explaining exactly why we can get away with memory order relaxed here, but I decided against it because it's quite complicated to explain. And at the end of the day, it doesn't matter so much, I think. If you just use a strict memory order here or any other type of order, you would probably still get away with it with minimal effects. So let's just not talk too much about it, but suffice to say, we can get away with it because we have relaxed synchronization constraints on the exceptions and when we can stop running tasks. So we can just ignore this for now and just return the value of the atomic Boolean. So if it's true, it'll return true. If false, it'll return false. Then we've got our set function, the set function on exception state. That will take an exception pointer as an argument, and it will store true into the atomic Boolean code error. Then we have to lock the mutex in order to move the exception into the exception pointer. That's all really to do, all there is to do. Then we've got reset, which is going to first move the exception into a temporary EX, store false into the error, set the exception pointer to a null pointer, and then return the temporary restored. So at the same point, at the same time, reset returns the last exception that was stored in here, and it sets it back to 0. So that's it, I think. We have successfully met all of the requirements that we had. We reutilize all of the machine resources with not too much overhead. We handle exceptions, we exit early. We built all of this ourselves without any external libraries. So the last slide actually pertains to a bug that we found recently. And it's an interesting one, so I thought I would share it here. I do not have the fix to the bug in the presentation because it would take another hour to explain, but I can point you to the fix on our repository. It's an interesting bug because it's a Stack Overflow bug, and it was quite nice to debug. And it shows that, yeah, there's always, this stuff is not super easy to handle. To understand the bug, first we need to understand the implementation of the parallel for loop. It's quite easy. It's a struct with a function called apply, which has the limits of the for loop left to right, the task system, and the function. And the way it's implemented is we create a task group with the task system as a pointer, and then we add all of the functions. We run them on the group, so we push them onto the task system, and then we wait for them to be executed, right? And when wait returns, we know all of the functions have been executed, and then we know that we're done. And the bug occurs when we nest these parallel for loops. This is one of the situations where it can occur. We've got an outer parallel for loop from 0 to 20,000, some arbitrary large number. And the function that is executing is another parallel for loop. This time doesn't really need to be a large number. Here I'm just doing it once from 0 to 1, and I'm just executing some task. And we could run into a task and into a Stack Overflow error here. To illustrate what's happening, we need to look at one of the notification queues, what's happening in there. First, we're going to go and we're going to try to execute this outer parallel for loop, right? So we're going to go and run for each of these tasks from 0 to 20,000. We're going to try to run this internal parallel for loop and then call g.wait, right? So notification queue will look something like this, 20,000 entries of the parallel for loop. And then we're gonna get to the g.wait, and while the thread here is waiting, it's gonna start to execute some tasks. So it's gonna go pick up the first parallel for loop, and then it's gonna go inside again, queue task onto the notification queue, and then wait again, right? And then when it calls wait again, it's gonna go pick up a parallel for task, queue task, wait again, so on and so forth until it goes over all of the parallel for tasks in the notification queue. But every time it's going and picking up a new parallel for task in g.wait, it actually needs to save the context of where it was called. So on the stack, it needs to save, oh, I was called from this task. Then I was called from this task. And we end up with this recursive loop where the stack can basically contain as many entries as the outside parallel for loop. And then we can get into a Stack Overflow. And the way to fix this is to use priority queues. And that's how we ended up fixing the issue. And you can take a look at it. I have some links in the end here to the threading library and to the pull request where the Stack Overflow bug was described and solved.